pretty much. So with that, we will throw it over to John. And in advance, we appreciate you, John, doing these programs. They're very informative, well done, and we appreciate you taking the time to do it. So I suppose if you can go, no more than an hour, it'd be good. And then we'll have our drawing and let everybody go. So it's over to you, and thank you in advance. Go ahead.
Okay, well, I'll push the present now button. And it should come up there. Share your entire screen. Okay. Now let's bring this up. All right, and go to the slideshow from the beginning. Now, is everybody seeing our friend here in bed?
Yes. Do you see that thing that says Meet.Google is sharing your screen?
Uh-huh.
Click on hide, because we can see that as well. It'll block anything that's there. Perfect.
There we go.
Sweet.
All right, skin effect. Now, this is a phenomenon that lots of hams have heard about over their career. And it's not that kind of skin effect that we're seeing there in the picture. I just thought that was a cute way to present it. But skin effect in ham radio, it's more important than you might realize, or at least it's more in the background than you might realize. Perhaps you've at one time or another in your career looked up at the wires on a big high tension tower like high voltage transmission tower, AC transmission tower, and wondered, why are the wires multiple? Why do they do them in bundles, and instead of use a single wire? I mean, some of them do use a single wire, but many of them use bundles like you see here. Well, it's simply due to a phenomenon that we know what we're talking about tonight, skin effect. Because small wires or smaller wires have less skin effect than larger wires. And therefore, if they use several smaller wires in place of one larger wire, they can push more juice down the line. And that's the reason why they're doubled up. But that's not the only place skin effect works. It works at all AC or RF frequencies. It's just rather important to power engineers, as it is also to ham radio operators. But who cares? It's one of those topics that, exists, but nobody really cares much about. And yet it has more effect on ham radio than we realize. So the objectives tonight of this talk is, where does it matter? Where are the places where skin effect pops up? And because I'm a physics type, that's what my university education was, in physics. I've always wanted to know why the skin effect exists even. So we're going to do a little fairly technical stuff here for part of this. And if you're not a physics geek, well, you can just kind of let this pass by. But you might also be like me and wonder, why in the heck does skin effect even exist? And I'm going to explain it to you in a way that I think you can understand it. And then, of course, I'm going to give you some practical examples of where it pops up in ham radio. All right, so here's where it's important. Here's where skin effect in ham radio matters. It plays a major role in the coax shield current that we sometimes have in our stations, that nasty stuff on the outside of the coax. That's a direct result of skin effect, as we will see. Also, skin effect is important in ham radio because it means that small, thin conductors have a benefit because of skin effect. Also, if you are ever making a loading coil, such as for your mobile HF station or maybe a wire dipole or in a beam, skin effect plays an important role in making efficient loading coils. Also, for the grounding of your station, we all kind of realize that you should have your station well grounded, and oftentimes don't realize what's the best way to ground it, the best conductor to use to ground it, or as the Brits call it, to earth it. I talk a lot to British stations since I spent a lot of time in England in the past. And so if you want to, how do you best to earth your station? And a very favorite topic with me, antennas that are made with foil tape. Now I know that's a new topic to many, and I talk a lot on that topic, but skin effect is very important in foil tape antennas, and it's a big advantage. Okay, let's get a basic understanding. This is where it gets a little technical, so if you want to sleep through this, go ahead. But I think I found it fascinating to find out why skin effect takes place. So first of all, what is it? Well, I think most of you will know what it is. It's the tendency of alternating current, and especially RF current, radio frequency current, which is of course also alternating current, to flow on the surface of conductors and not to flow on the inside, or not to flow so much on the inside of a conductor. Here's a little graphic of it. That's a piece of wire cut in half, and looking at the end of it, and the red represents the RF, or flowing on that conductor, and more intensely on the surface and less intensely as you move inside. As a matter of fact, at radio frequencies, that skin is much, much, much thinner than you see it here. I've only let it be bigger so for the graphic. And what's the effect of the skin effect? Well, fundamentally, the major thing that skin effect does, it reduces the efficiency of the conductors, either requiring you to use bigger conductors or to make the conductors that you have more resistance, which is not very good, particularly in small antennas. Here you see it represented a little more accurately. This is a drawing, which was in your newsletter there or your website, of a piece of aluminum tubing, which you can see partly in gray there, and the RF skin current on it, which, as you can see, only penetrates even to that thin aluminum tubing a short distance. So let's take a little sidetrack here. This is a little physics. As I say, I did physics at university, and so I like physics explanations. But so did Einstein. But he didn't like all the math. He didn't like all the partial differential equations. He left that to his wife, who was good at math, and he was good at it too. He wasn't bad at math, as some people say, but he liked to visualize, and that's what I like to do. I like to visualize physics, not write formulas for it. Okay, let's understand it visually. Here's a piece of wire on the left with a current flowing through it, I, the current, typical symbol for the international symbol for current. And around that wire, any wire carrying current, is a magnetic field, or we call it flux, magnetic flux. That's the actual technical term for it. It surrounds the wire. And if you're familiar with the famous old right-handed rule, the direction of the magnetic field around a wire, if you use your right hand and point your thumb in the direction of the current, is indicated by the direction of your fingers. That's an interesting way to remember the magnetic flux around a wire. Way back in the 19th century, all of this was first understood by notables like Michael Faraday, who studied magnetic field a very great deal and studied small loop antennas. It was discovered back there that and easily demonstrated. Piece of cardboard here with a wire running through it, some current in the wire, sprinkle some magnetic filings on the wire and on the cardboard, and they'll line up showing you the magnetic field. And this was understood 150 years ago. But now this is just a metaphor. This is not a reality. So this is just an analogy here that I'm showing you. But it's a way to help you understand why skin effect takes place, if you want to know. If you don't want to know, well, just sleep on. But anyway, imagine that this whole circle, the big circle here, is a piece of wire, a solid piece of wire, and that it's formed with a bunch of concentric sleeves that make up the wire. But that each of the concentric sleeves is actually made up of many, many fine wires. Here symbolized by only six wires, one in the middle and 5 on the outside. But imagine that whole piece of wire made up of all those little fine wires. In fact, an infinite number of them. Now, here's the point. So imagining that the solid wire is made up of a concentric bundle of single wires. Each wire, each of those single little infinite wires in that solid piece has a magnetic flux around it. That's what it would happen. If a wire carries electric current, it has a magnetic flux around it. And here you see just two of the imaginary little conductors inside one big one, and the flux around them. Now, what happens is the flux around each of those imaginary little wires inside a big wire links together, or combines or adds together. So those blue flux lines add together if they overlap. So the right conductor is inducing some current in the inner conductor, and the flux from the inner conductor is inducing some current in the outer conductor. This is what happens inside of a conductor. These are the flux linkages that take place in any conductor, be it a piece of wire or a square piece of metal or whatever. The fluxes in any conductor add together. However, since the conductor is not infinite in size, the addition of these fluxes isn't equal. Some of the flux in a round conductor here, such as the one at the outside, doesn't link because it's just out in space, whereas it links on the inside. So the point of this is that the flux, the magnetic flux inside of a conductor, be it a piece or a sheet of wire or a copper wire, is most inside the conductor. So the flux linkage that takes place in any conductor is greater inside the conductor. So realize that. Flux magnetic field is greater inside all conductors due to flux linkage. Least on the outside, because on the outside some of the flux escapes. Therefore, the total magnetic flux in a wire, and I know this is physics stuff, but total magnetic flux in a wire is stronger on the inside. And so is the inductance. Now, you probably all know that any wire has inductance. That's what makes it able to become a coil. And that inductance that's in any wire is directly proportional to the flux. That means the higher the flux, the higher inductance. That's the basic rule of physics. So there's higher inductance inside a conductor. So the inductance of a wire is higher on the inside than it is on the outside, and making up the total inductance of the wire. Therefore, the inductance offers greater resistance, or reactance as it's called, X sub L, on the inside of the wire. So lodge this point. The resistance of the inside of any conductor is greater to alternating current because of flux linkage than it is to the outside. So that less current can flow on the inside that can flow on the outside because of the higher reactance of the higher inductance caused by the flux linkage. I know that's a mouthful of physics, but that's how it happens. And when I saw this the other day, I thought, that's interesting. Now I know why skin effect occurs. So greater the AC resistance inside due to greater flux linkage, the less the current. And that's what causes skin effect. Okay, enough physics. Some of you might enjoy that. Some of you might have put it to sleep, but that's all right. I thought you might like to see it. Let's now look at the practical consequences of skin effect. Here's a diagram, a schematic diagram of a piece of coax coming in from the left there. The horizontal structure there is a piece of coax cut in half. So you can see the outer conductor, the dielectric, and the inner conductor. And it's connected to a dipole, which is the wires running vertically. It's a simple dipole. The basic action of the coax is to deliver power to that dipole. So the red and the blue are the desirable currents coming from the transmitter, feeding the dipole on the outside, running up and down inside the dipole, into the dipole, up the dipole and back, and then back down the coax. But all of that we want to have happen on the inside of the coax. We don't want any of that happening on the outside of the coax, but unfortunately it does if your baluns aren't correctly positioned and they aren't of the direct type. And why is it a problem? Because the shield of the coax, now don't miss this point, the shield of the coax is actually two conductors due to skin effect. Because of the skin effect, there's a current path on the outside of the shield, and there's a current path on the inside of the shield. And the current on either one of those can flow in either direction and be different. Also, at the end of the coax, also because of skin effect, those two conductors in a shield are connected together wherever coax ends. I call it the 2 to 3 wire transition. Remember, never forget it. Coax is a 3-wire transmission line, not a 2-wire transmission line. It is a 3-wire transmission line because of skin effect, causing the outside of the shield to be a separate conductor from the inside of the shield. And we don't want this to happen. That's why we have balance. By the way, I hate it when somebody says, what's the primary purpose of a balun? And answers, oh, that's to bring unbalance to balance. That doesn't mean anything. The primary purpose of a balun is to get rid of the shield current on coax. Because of the 2 wires that any coax is, because of skin effect, you can get RF on the outside of the coax at wherever the coax ends. And that's what we don't want. And why don't we want it? Because it disrupts the SWR of the antenna and the whole system, because it's part of the antenna. It's an extra wire that gets added to the antenna, and it disrupts the SWR. It also disrupts the tuning. It might throw the antenna off frequency, which it readily does if the balun isn't right. And worst of all, if you don't have the balance correct, the radiation pattern of your antenna may be terrible. You may think it's going towards the horizon when in fact it's only warming up clouds or heating up worms. Skin effect is very important. It causes this to happen. So remember, outside shield current, which is to be removed with a balun, is caused by skin effect. All right, that's one consequence. Enough on that one. Now, a second consequence of skin effect. It is the value of thin conductors. And thin conductors have an advantage because of skin effect. Here's the skin depth that's caused by, that happens at RF frequencies, the bands on the left there, typical ham bands, caused in aluminum and in copper. Notice how thin it is. These numbers are thousandths of an inch, or mils. Even where skin effect is the worst for ham radio on 80 meters, on HF anyway, on 80 meters, the skin depth is in aluminum is the worst case is only 1.7 thousandths of an inch. That's very thin, even at 80 meters where it's worse. Copper, it's even thinner, 1.4. At 70 centimeters at the bottom, or 450 megahertz, the skin depth in aluminum is only 2/10,000ths of an inch. Very, very thin. So remember, that skin at RF is thin, but that's an advantage actually in one place, as we shall see, although a disadvantage in another place. That means that thin conductors suffer less from skin effect than thick conductors do. Notice the thicker one at the top. About half of that wire, that conductor, is being wasted. The thin conductor at the bottom is carrying the same amount of current because the skin effect is the skin depth is the same, but there's no wire wasted because of skin effect. The one in the middle is in between. This means that if you're putting up an antenna made out of wire, make it out of stranded wire. Don't make it out of solid wire. If you make it out of solid wire, your dipole will be less efficient because there will be more resistance in that conductor, in that wire, than there would be if you made it out of stranded wire. Many hams don't even know this. They just think, oh, I'll grab myself a piece of number 12 solid wire, makes great dipoles. Yes, it makes a great dipole, but it's less efficient than if you made it out of stranded wire. If you're making loading coils, like for your mobile or for wire antennas, stranded wire is the thing to use, not solid wire. There are two patterns for stranded wire. the 7-strand, which you see here on the left, and the 19-strand, which is, it's a stranded wire is made in one of these two patterns because it's geometry. 7 strands fits together nicely, and so do 19 strands. 19 strands is seven strands in the middle and 12 strands on the outside. Makes a nice round bundle. So all stranded wire, and wire, rope, and cable, by the way, are made the same way. Now, if you're going to make yourself a wire antenna, go buy some of this. It's called Davis Polystealth. This is the best wire to make wire antennas with. It's 19 strands. It uses the 19-strand pattern of a wire with a steel wire on the inside plated with copper and 19 strands of it. So it's very efficient in its ability to conduct current, and it's very strong. Comes in several sizes, 28 gauge at the bottom. I think it comes in 13 gauge and something else. I've had a loop antenna around my house up for 2 years, made out of 28 gauge Polystealth wire with a beautiful polyethylene jacket on it. It hasn't stretched an inch. By the way, 19-strand wire is stronger than 7-strand, but it's less flexible. Just for interest's sake, some of you may have heard at one time of Litz wire. It's not used so much anymore, but it's another way to make stranded wire more efficient, carry more current. It's actually 7 bundles of 7 strands, and that's an interesting pattern. You don't see it too much these days. It used to be used more in the past, but it's the most efficient way to make a stranded wire to carry current. That's because there's equal flux linkage in all the wires inside of Litz wire. It's more of a historic note. All right, another consequence, loading coils. Here's a loading coil, a symbol of one anyway, piece of PVC pipe maybe, and 5 turns of solid wire wound as a loading coil. Notice what happens to the RF current when you place the turns on a loading coil right next to each other. It's called adjacent turn skin effect. Notice that because there is flux linkage now between adjacent conductors, all of the current there rushes away from the flux linkage and up to the top or the bottom. So if you put the turns on a coil close together, the coil is less efficient, has higher resistance. And that's why winding close together turns on a loading coil is not a good idea. It's bad to put the turns on a loading coil close together. You want to space them apart. I recommend that good compromise is a 1-to-1 spacing, where the space between is equal to the width of the wire. It doesn't get rid of all of the adjacent turn skin effect, but it gets rid of a good bit of it. 3-to-1 is what you got to do if you want to get rid of all of it. Anyway, for example, here's some inefficient loading coils and an inefficient coil in a trap there on the lower bottom right. On the lower left is a loading coil, or is it loading coil or a coil made with looks like 12 gauge wire, enameled wire, wound on a form, solid wire wound on a solid form right next to it there. That's an inefficient loading coil. The ones at the top, you might say, wow, those are the Hustler loading coils that I use on my mobile antenna. Believe me, friend, they are not high efficiency loading coils. Why? Because they're solid wire wound right next to each other. Now, some companies in the past have made better loading coils than that, but they're not very popular anymore. And on the lower left, right there, is a trap made out of a coil, which is easy to do, as some of you may know. And it's an inefficient trap because it's using, again, solid wire wound close together. Here are a couple of good loading coils with a 1-to-1 spacing. That's an MFJ loading coil on the left, a commercial one that you can buy. The one on the upper right, I don't know where it comes from, but it's a good loading coil, adjustable one with a 1-to-1 spacing. And on the middle bottom there is a good homebrew loading coil with a nice design. I guess somebody is using it in their dipole made out of aluminum tubing. As these are good, reasonable compromise loading coils because of skin effect adjacent turn. And here are 2 very efficient loading coils, again, homemade. One on the left looks like about a 2-to-1 spacing, and the one at the bottom looks like about a 5-to-1 spacing. These are efficient loading coils with very little additional resistance caused by skin effect. All right, grounding, or earthing as the Brits call it. Most of you know that it's a good idea to ground your tower and ground most of your equipment in your station. But if you do so, use flat strap made out of fine wire braid. That's the best. It handles the current the best and does the best job of grounding. Solid round wire can be used, but you need a lot more of it to do the job, as well as this flat stranded or stranded wire braid. Okay, the last consequence here. Foil tape antennas. This is one of my favorites. I like to make antennas with aluminum or copper foil tape because it makes some great antennas. And here's what I make it with. This is copper foil tape on the left that you can buy on the internet readily or get at your local garden store to keep snails out of your planters, or aluminum adhesive tape, which you can buy at any almost any hardware store. It's used for taping up air conditioning ducts, and it's available readily on the internet in all sorts of thicknesses and widths at quite a reasonable price. It is a great material for building antennas. Here's one kind of an antenna you can build with it. This is a cardboard tube that you can get down at your local builder store for about $15, I think they cost. It's 12-inch diameter cardboard tube that builders use to pour concrete inside of to make posts out of. But it makes a great loading coil for using in a high efficiency loading coil for use in an attic where it's nice and dry, because there the cardboard will last just fine. And as you notice, it's made out of 1-inch wide copper foil tape, spaced 1 inch to get rid of the adjacent turn effect, and it's got some short copper tube extensions on the end. This is a 40-meter antenna, which is 1/3 the length of a full-size 40-meter antenna. Therefore, it can go into many attics without bending and folding it all over the place. Now, some people may say, well, isn't copper better than aluminum to use for coils and stuff like that? No, it's not. And the reason is, even though aluminum has 40% less conduction than copper, 40% less conductive than copper, it has twice as thick a skin. Therefore, the total effect is that aluminum and copper are absolutely equal building materials for building loading coils or foil antennas. Where this really comes to bear is if any of you happen to build magnetic loop antennas. And this is a favorite of mine and a favorite for a lot of hams. And here are a whole bunch of them that I took pictures up off of the internet. Some of these are terrible designs, and others are pretty good designs. Skin effect is something that you can really take advantage of in a loop antenna, in a magnetic loop antenna, a small one. The magnetic loop antenna, by the way, came to popularity as recently, only 1968, when Lou McCoy, in the 68 issue of QST, using a design that he had seen from an Army engineer, published this article on the Army loop, which is still available. You can get it up from QST if you want, from the article archive. And it was a 12-foot diameter octagonal loop made with aluminum pipe, 5 feet sections, 5 feet long, and 45-degree elbows matched with a couple of 3 tuning capacitors at the bottom. Some of you may have made magnetic loops, which is what this is, and so forth. And it was from this article that it pretty much got its start. It's now a very popular antenna, almost as popular as the infamous copper J-pole for 2 meters. Though that loop, though it's stuck in the mind of many, many hams, is not the optimal magnetic loop. This one is. This is an optimal magnetic loop. Has all of the characteristics of the magnetic loop optimized. And notice, it's not built out of copper pipe. It's built, of all things, out of PVC pipe. But because of skin effect, all you need to do to make PVC pipe just as good a conductor is give it a coating of aluminum foil tape, which you can see here. By the way, the tape's also inside the elbows. So here is a maximum efficiency loop, square, because square is just as good as octagonal. You don't need to make it round or octagonal to make it good. A square is the easiest way to do it. And you see the matching network there at the bottom, which is, I think, the optimal way to do it. But notice, skin effect enables us to use aluminum foil tape to make PVC pipe as good as heavy, expensive copper pipe. Don't build your magnetic loops out of copper pipe. Build them out of PVC and foil. And here's the foil being put onto the tape. This is the way I do it. I stick the ends down, put the pipe on the sticky surface, and roll it back and forth. Takes 2 overlapping strips of 4-inch tape to cover the pipe. Works well, though. And here are the corners. The foil goes inside of it. It takes a little doing to get it neatly inside of it, but it's not too hard to do. Just cut a little L-shaped section and sort of manage and use your fingers and press it in. And so as the pipes make contact with these round edges with the holes in them, it makes good contact held together with sheet metal screws. So in closing, and then we'll end here, skin effect may not seem like of an important topic to ham radio, certainly not an everyday ham topic, but as I think you've now seen, it has more impact on ham radio than a lot of hams realize. And here's my little doggy, Lolly. No, she does not have a German call sign, D0GGY. I just like to pretend that she does. If you want to get a hold of me, you can get a hold of me there at W6NBCmail@gmail.com or at my website, W6NBC.com, or through that QR code that you see on the upper left. And that's it, folks. Skin effect.
Okay, John. That's great. That's very that last loop you showed there, the square. That's very interesting.
I do a complete talk on it if you want to hear that later.
I don't know why not, but sure. Okay. I'm going to ask, since are there questions for John first, and then a couple other things I'd do here. We got a little time. Any burning questions? No. Okay.
You got a hand raised there by Barbara. Sure.
Barb. Okay, Barb.
If I could be John, if I could ask you to put the screen up so I could take a picture of the square.
Oh, well, yeah, just take out a pencil and write my email down.
Okay.
Several steps to get it back up again. My email, W6NBC, my call sign, mail, W6NBC mail at gmail.com. There it is, W6NBC mail at gmail.com.
Okay. That
And,
works. Thank you.
I'll be glad to correspond with you and answer any of your questions offline, or start up another Google Meet session with you, and we'll talk about it.
Okay.